Come on in, everyone. More people coming. All right. I might have more students in here tonight. I had to, I got a flat this morning. I had to cancel my morning classes and my morning lab. So, or I should say my lab. So we might have some students from that coming in. I'm not sure. I was so busy with dealing with the flat tire that I didn't even get to send the Zoom meeting out to my other class until about 5 minutes ago. So nothing like waiting till the last minute for them. Seems to be a trend within my life. That's how I roll, yo. And I think I have some. Oh, that's what I want. I think we're gonna have to create another page. Get away from here. Okay. Give me a buttload of stuff first. All right. Anybody have any questions before we get started? I can go ahead and unmute yourself. That'd be great. All right. Got somebody else coming in. That's not what I want either. No. Getting emails all over the place. So nobody has any questions about anything? Let's see what this one looks like. Oh, good news. This one. Okay, now I see. All right, we'll make a new notebook. I think I'll call it. Today is what day? Today's the 15th. Sorry for taking so long, everybody. Anybody? I've asked if anybody had any questions. It seems like nobody has any, so I assume that's cool. 241, and this is in 01. We'll see. And I'm gonna do underscore. If I can find my underscore. Where's my underscore? That is not my underscore. Here it is. So today is 06/15/22. So there you go. All right. So last time we actually finished chapter 5, I think it was. Yes, 5. And this time we're going into Newton's law of gravity. I'm going to tell you basically how it panned out. Basically, Newton was sent home during the plague. And during that time, like all good college students, he, of course, went to Cabo and went to St. Thomas and all sorts of cool stuff. Got drunk, drank a bunch of beer. No, none of that, actually. Okay. So actually, he went home to his apple orchard, and he wrote in his Principia that he was sitting in his apple orchard, and he looked up at a tree, and an apple tree, and saw what the apple and the moon had in common, which right off the bat, you know, he's not wrong. Okay, you don't do that. But anyways, he did do that. And what he meant by that is eventually that apple is going to get nice and juicy, and its weight will be a little bit heavier than its stem can hold, and the stem will break and it'll fall to the ground. And he wondered, or in fact, he said, I wonder if that force that's pulling the apple from the tree is the same force that's making the moon violate Galileo's first law of motion, or seem to, because Galileo's first law of motion is, which was later called Newton's first law of motion, but was called Galileo's law of inertia, basically said an object in motion tends to stay in that state of motion unless acted upon by an external force. We had the moon, which appeared to be going in essentially a circle around, even if it was going at a constant speed, which it doesn't exactly, it's pretty close, but not. Okay, even if it was going at a constant speed, that would still be not the same motion, because changing direction is a changing of velocity, even if you keep the same speed. So he knew it was accelerating. And in fact, he had used the calculus to calculate, and you don't need it for that, but it's quite easily done with the calculus. He had found out that the centripetal acceleration required to actually cause the moon's orbit was v squared over r, where r is the distance from the center of the Earth to the center of the moon, and v is essentially the average velocity or speed. Now, if you actually use v squared over r, that is the centripetal acceleration. And that acceleration should be the same thing that is the acceleration of our apple on a tree. Only in that case, the apple is only 1 Earth radii from the center of the Earth. And he knew that the moon was 60 Earth radii from the center of the Earth. So he said, well, gravitational acceleration, probably didn't use these units, but either way, gravitational acceleration is 9.80 meters per second per second. If I assume that gravity is like light, he had been studying light, he had wrote 500,000 words, I think, on optics, and he had studied light, and he found out that light decreases by a distance squared. So if you have a light bulb, say you're 3 meters away from it, it's a certain amount of brightness. If you move, instead of 3 meters, you move 6 meters, that will actually go down by a factor of 4. The brightness will decrease by a factor of 4 because you went up by a factor of 2 distance-wise. If you go, instead of 3 meters or 2 meters or 4 meters, if you instead go 6 meters, then you've gone a factor of 3. And in fact, that would reduce the brightness of the light by a factor of 9. So if you go from 1 Earth radii to 6 Earth radii, you would expect 9.8 to go to 9.8 divided by 60 squared, which, if I remember correctly, is about 0.02. Actually, I got my calculator. Let's go ahead and do that. 0.0258, or I think that's what I'm remembering. So 9.8 divided by 3600, 0.002722. So that was the acceleration that he found that the moon should have. And then he did a calculation of v squared over r. And v, of course, is 2 pi times the radius of the orbit divided by the period of the orbit, which is about 30 days. He computed that, squared it, divided it by r again, and lo and behold, he got 0.00272. Okay, so at that time he knew, and he was the only person on the planet that knew exactly why the planets circle the sun, and why the moon circles the Earth, and why the Galilean satellites circle Jupiter. So it was a really big deal. And basically what he came up with was Newton's law of gravity, which is a 1 over r squared force. It says that the force of gravity is inversely proportional. That means thumbs up, thumbs down, meaning if your distance between the 2 planets goes down, your radius, your force goes up. And if the distance between the 2 planets goes up, then your force goes down. Not by a factor of 2 if you double it, but a factor of 4. If you triple it, it'll go by a factor of 9. If you quadruple it, it'll go by a factor of 16. If you quintuple, it'll go by a factor of 25, so on and so forth. He was also able to determine that it should be directly proportional to mass. And that meant, in fact, that gravity actually acts on everything. It's just such a weak force that you don't notice it until it gets, planet-sized masses or moon-sized masses. What he discovered was that the force not only being inversely proportional to the square of the distance between them, it turned out to be directly proportional to the product of the masses. That means thumbs up, thumbs up. So if you doubled the mass of the sun, the force of gravity on the Earth from the sun would double. If you doubled the mass of the Earth instead, the force of gravity on the Earth would double as well. But if you, let's say, tripled the mass of the sun and doubled the mass of the Earth, then you would basically increase the force by a factor of not 5, but 2 times 3, which is 6. Okay, so that was that was Newton's law of gravity. And he admitted, I have no idea how this possibly works. It's as if basically some tentacle is reaching out across space and we can't see it, but it's reaching out across space and grabbing onto the planets and holding them near us. I think I knocked Nora down. Anyways, so it was like something's reaching out there. That's called action at a distance. He knew it was a problem. Everybody's known it's a problem since then. In fact, people knew it was a problem when they were studying electric forces and magnetic forces, which turn out to be way stronger than gravity. But again, they pressed on. And the way they solved that in electricity and magnetism was they created the idea of a field. And that's sort of what they did with gravity, but ultimately Einstein has to come along and fix it. So let me start off by showing you Newton's law of gravity and giving you some of the details about it. So first off, I'm going to share my screen with my iPad, and we're going to hope that this works again. And that's going to be via AirPlay. So I have to do this, and then I got to tell it to do something, and blah, blah, blah. So screen mirroring on Zoom on my Mac, got it there. Okay, that's done there. So the law that Newton came up with was that force, okay, I guess it's not going to be right. Okay, let's see if it works now. This could be bad. Why is it not letting me write? Let's see. I want a different color. Let's try black. Okay, so evidently the pencil's not responding at all. Okay, that seems to be working. Let's do a Bluetooth thing to make sure it's connected. Sorry about this, folks. Technology, it's great, right? Anybody use GoodNotes, know how to get your pencil connecting to your pad? All of a sudden, I seem to have forgotten or something.
Sometimes what I do is I just connect. Do you have the newest one where it connects to your iPad to charge?
Yes.
So I just usually reconnect it and let it sit there for a second, and then try to rewrite on GoodNotes.
Okay, I've got it sitting here for a couple seconds. Let's see if it does now. Thanks for that help. Hopefully, that's what I thought I did. Anyway, it's still not writing. Any other helpful advice?
Are you in the pencil setting on that app?
I have it sit on the fountain pen.
Oh, okay.
Maybe.
Yeah, sometimes if it's on like the arrow one, then it won't work.
Or if you're on
it's not doing with the highlighter, not doing with that. So yeah, it's definitely not connecting to whatever it is.
What color is it?
It says it's currently baby poop yellow.
Okay.
It's the grossest looking color I've ever seen. If I can put a fine tooth comb on it.
All right.
Okay, so that's not helpful at all. That didn't help. Go away, you. Okay, that didn't work. Boy, it's a pleasure to watch my mind at work, isn't it? Let's see if I can find anything about pencils. Good page. Good. Still got nothing here. Let's try this. No, that's nothing. Nothing there. It won't even let me like choose a pen color that's cool. Let's try custom black. Let's see if it writes now. No, it's still not writing. Anybody else have any fabulous ideas? Maybe my Bluetooth's off. It recognized my pencil when I put it down.
What is your pencil charge at?
On a little holder in the side of my iPad OtterBox.
No, percentage wise.
Oh, it's 100%. Let me double check again. Yep, 100%.
In the left-hand corner, or the right-hand top corner of GoodNotes, there's an icon that has a pencil with a line through it, or a pencil with like a circle around it.
Mm-hmm.
If you see a pencil with a circle around it, then click it, because it's not going to let you write unless that's clicked. It's like an edit mode.
Okay, gotcha. So that should appear when I pull my pencil out, right? Because I don't see it yet. Oh, there it is. I got a pencil with a X mark through it. It was like, I thought it was an X mark all this time. Nope, still not ready. Let's try this. Okay, that got rid of that. That didn't help it. And you said it's top right and it's supposed to be a pencil like in a circle or something?
It's supposed to, I think you have it right. It's supposed to be a pencil with a line through it.
Mm-hmm.
If you see that, then that's not the issue. But if it has a circle around it, then that's the issue.
Okay. Yeah, it looks like I now have the circle around it, but it's still not letting me write. Ugh. I don't know why this is happening.
If it's an application problem with
Mhm.
GoodNotes, then you might be able to go to your Notes app in your iPad and write there
Okay.
instead. I mean, unless you want to really use GoodNotes, but you can download what to take on the Notes app and put it into a Google Doc if that's what you need to do.
Gotcha. I can try my notes. Let's see. Gosh, I'm sorry, guys. Let's try this.
It's all good.
I got all sorts of notes up in here. Let's do a new note. How about that? Yeah, this is going to be
And
bad.
then you want to press
Well, let's
the the button in the top right in the middle that indicates a pen. You want to press that,
Okay.
and then you
Oh, I
want to
see.
draw with your pen.
Gotcha. It'll just take straight right in there.
Yeah, but you want to go to the bottom there, and you see how there's an A on the
Right.
pen that you've selected. That means that you're texting. So you want to press the button beside it that puts it on the pen mode.
Okay, gotcha. So you're saying this little A in the bottom right where it says AA?
Yeah, you don't want that. You want to select the pen beside it.
Gotcha.
So now you got to go back up to the top, press the pen button at the top right.
Okay.
That means you're in note mode. So now you have to press the second pen
Oh,
because
gotcha.
that's the one that you actually write with. And
Gotcha.
now you should be able to draw it.
Okay, that's cool. Thanks. Appreciate that.
Mm-hmm.
All right. So what Newton said was that F, that will not let me write again during you. I got this one. I got that one. Oh, but it's trying to write. I saw something up here. No, it's not doing crap. Okay.
Oh, no.
Yeah, that just died too. So
Is your pencil tip screwed on all the way?
you know, it does look kind of loose.
Oh no. Courtney, you get a raise.
Let's see now.
Watch this work.
Oh wow, right. It's an amazing world we live in.
Oh my god, imagine.
Glad to be able to fix that
Good
problem.
job, Courtney.
Good job, Courtney. Appreciate that. All right. So what Newton said was F is directly proportional. That's a symbol we use in physics for proportional, by the way. It looks like a fish, okay? A fish with part of its tail missing. Directly proportional just means you put them in the numerator. So it's directly proportional to the product of two masses. One of them is M1, one of them is M2, and then it's inversely proportional to the square of the distance between them. Okay, now what he said, and this part was important as well, the distance between them is the distance between the center of mass M1 and the center of mass M2. And he said the force was attractive and acted along the line connecting those centers of mass. So by doing so, even though vectors hadn't been invented yet, he in fact gave us enough information to know about vectors. So we can now tell the actual direction. So all you need when you have a proportionality like this is from, high school algebra 1 stuff, where they say, X is directly proportional to Y. When X is 4, Y is 18. What is K? And then they'll ask you, okay, well, what is Y when X is 3 or something like that? All you have to do is that one experiment or give you that one piece of data where you fill in this case, M1, M2, and R, and that will give you, if you know the force, that'll give you what the constant is. So it turns out this constant is called the gravitational constant of the universe, and it's a capital G, and then it goes M1, M2 over R squared, where G is equal to 6.67 times 10 to the negative 11th. Notice I've got to have newtons on the left-hand side, so the unit of this has to have a newton up top. It's got to cancel out 2 kilograms, which are also on the top, so it needs to have 2 kilograms on the bottom, so it'll be kilograms squared. But it also has to cancel out 2 meters that are in the bottom, so it's got to have meters squared right here. Notice how small that number is. It's 0, followed by a decimal point, followed by 10 zeros, and then a 667. So that's a pretty small number, and that's in fact why gravity is in fact the weakest force. Now, they also call it universal force of gravitation, and a couple reasons for that. One of them is because it seems to be true all over the universe. It's true for any 2 objects that have mass. So in that sense, it's universal. But also notice there's no value of R for which this force truly goes to 0. So the force might be weak, but it has infinite reach. It can reach all the way across the universe. So that's a couple reasons that it's called that way. Now, just to give you some perspective, the what's called the Coulomb Force, that has the exact same form. It has a constant. Actually, I don't like this version of the constant, but that's the easiest one to write. It has a different constant K, and instead of mass, it has charge 1 and charge 2, but it still has 1 over R squared. But check this out. That K is 8.99 times 10 to the 11th Newton meters squared. And instead of kilograms squared, it's Coulomb squared. So you can see, excuse me, 8.99 times 10 to the 12th. Sorry about that. Let me pretend like I know what I'm doing and get my eraser. Yep. Oh, that worked good. Yep. Oh, awesome. So evidently 8.99 times 10 to the 9th. Sorry about that. There you go. So you can see, just comparing those constants, if you divide the K by the G, you're going to get a factor of 10 to the 20th. So literally K is on the order of 10 to the 20th times G. But in fact, if you did a simple problem like comparing the charge attraction between a proton and a neutron and a proton and an electron and a hydrogen atom, and compare that to the gravitational force, you're going to get on the order of 10 to the 43. So it is a really, really monumentally weak force. Imagine the Coulomb force, which is the force of attraction when 2 charges are opposite, or repulsion if they're the same. That is 1 followed by 43 zeros times stronger. So that's actually Newton's law of gravity. From that, we can do all sorts of stuff. We can calculate what kind of forces are acting on things. So let's, for instance, take the idea of a atom, for instance, the hydrogen atom, and let's calculate the attractive force. So the atom, so hydrogen atom, I just barely made it to class on time too, because my internet was out. So I literally had to restart my router and everything. I'm lucky I got here, long enough to waste 20 minutes figuring out that my pencil was unscrewed. So, so with this, you have the mass of the electron, which is 9.109 times 10 to the negative 31 kilograms. And you also have the mass of the proton, which is quite a bit bigger. It's 1.607 times 10 to the negative 27th kilograms. And then you have the Bohr radius, which I'll call R sub B. It's the distance between them. It's 0.529 times 10 to the negative 10th meters. So we can now calculate the actual force and say the force of gravity between the proton and the electron, okay, just as magnitude now, is 6.67 times 10 to the negative 11th. Notice what I do with the unit. I keep it so I can make sure everything looks right. 6.67 times 10 to the negative 11th Newton meter squared per Coulomb squared. Now I've got to take 9.109 times 10 to the negative 31 kilograms and multiply it by 1.607. I probably should check that. It's been a long time since I looked up the mass of a proton, times 10 to the negative 27th kilograms, divided by 0.529 times 10 to the negative 10 meters, and that's got to be squared. So I'm going to calculate this. I'd like you guys to do the same thing, but I'm also going to look up something on the internet and send out mass of the proton, just make sure I got that right. I'm pretty sure, but sometimes just, yeah, 1.67 times 10 to the negative 27. That's good. All right, so here I go. I'm going to take 6.67 e to the negative 11 times 9.109 e to the negative 31 times 1.67 e to the negative 27. And then I'm going to say divided by, and here's where I'm going to use parentheses just to be safe, because if you type in 5.529 times 10 to the negative 10th times 0.529 times 10 to the negative 10th, it would divide by the first one and then multiply by the second one, so you cancel each other out. So that's why I make sure I put a parenthesis in there, 0.529 e to the negative 10, and then I'm just going to use a square button that prevent all that anyways. And I get 3.625, so I'll call it 3.63 times 10 to the negative 47 newtons. That is super, super, super small. To give you some perspective, here it is for the Coulomb force. So again, this constant is about 9 times 10 to the 9th Newton meter squared per Coulomb squared. So it's that. Now, in this case, the electron and proton have opposite charges, but they're the same in magnitude, which is 1.602 times 10 to the negative 19th coulombs times 1.602 times 10 to the negative 19th coulombs over 0.529 times 10 to the negative 10 meters squared. Notice, just like before, the kilogram times the kilogram in the top canceled out with the kilogram squared in the bottom of the constant. And the 0.529 times 10 to the negative 10th meters, when that's squared, that canceled out with the meters up top and gave us, of course, newtons. So I'm going to say so I did 8.99, essentially the same thing as 9. 8.99 times 10 to the 9th times 1.602 times 10 to the negative 31st squared. Now I'm going to divide that by parentheses again for the same reason I told you before, 0.529 e to the negative 10. And then I'm going to square it. And this time I get 8.24 times 10 to the negative 32 newtons. So if I take F Coulomb PE and divide it by F PE gravitationally, you'll get 8.24 times 10 to the negative 32 newtons divided by 3.63 times 10 to the negative 47 newtons. And I get 2.27, whoa, Nelly, times 10 to the 15th newtons. Or excuse me, there's no newtons on that. It's actually unitless because I divided a newton by a newton. And actually that looks terrible. I'll trace it a little better. I don't know why I was remembering 44. Must be something else. I think I might have been thinking about the strong force. But anyways, that's how the force is related. Obviously, you could have done that symbolically, And what you'd end up getting is at least the R's would cancel out. So you could have just did the formula for FPE with the G and the M and the M and the R squared, and the formula for FCPE, which would be the K and the Q1 and the Q2 over R squared. You could just divide them out like that, or vice versa, flip it over. And the R's would at least cancel out, and you get exactly the figure too. But the main thing is you can see, yeah, clearly the gravitational force is kind of weak. Any questions on that and how that was used?
Yeah, I have a quick question
Yes.
for the Coulomb's force.
Mhm.
I understand that we're using a different constant, but why were the two charges changed? Are we doing it between two protons then?
So
or two
yeah.
electrons?
So what happened was when we did the gravitational thing, it turns out the proton is super, super heavy, whereas the electron is really, really light. And the proton's about the same weight as the neutron, not that far off, but the nucleons are really, really heavy. So that's why they have 10 to the negative 31st and 10 to the negative 27th. But mass is all that matters when you're talking about gravity. So that's why you're using that in the gravitational formula. In the Coulomb formula, you're using the charge, which y'all haven't learned anything about, so it's perfectly understandable to not know anything about it. But a Coulomb is really a big unit of charge to begin with, and both of them have the same charge. They're equal in magnitude, but opposite in sign. So the proton's positive. The
Okay,
electron's
so
negative. What's that?
oh, so it's between a proton and electron still.
Exactly.
We just ignored the sign because we're just trying to find the force between them, the magnitude of
Yeah,
force.
and not only that, when you actually do get to the second semester, you're going to find that it's a lot easier to first calculate the magnitude and don't do anything with signs. The only time you really use the signs is when you're doing like integral calculus to solve it. You don't want to do that. I mean, we're going to do it next semester, but you don't want to do it any more than you have to. Does that make sense?
Yeah.
Okay.
Okay, thank you.
No
That
problem.
makes sense. Thank you.
Now, you guys are sort of, I mean, I know you probably have some experience with vectors from maybe your pre-calculus class, hopefully, or your trig or whatever. This is where the algebraic stuff begins. So I want to give you an idea how you might solve an algebraic problem. And then I'm going to also take the time to show you a sort of brute force way you could really use. So for one thing, if you want to find a vector, you can always take the coordinates of the head of the vector and subtract from it the coordinates of the tail of the vector. And that will give you a vector that points from the tail to the head. All you have to do is just subtract, x from x and y from y and z from z. And then instead of them being, three numbers, now they're going to be an x component, a y component, and a z component. So you might say, let's try a problem like this. I have a coordinate system I'm going to draw this way, say. That's my x-axis. That's my y-axis. I'm going to have a mass here, M1 is equal to, let's say something kind of easy. Let's say 4 times 10 to the 5th kilograms. And then over here is mass M2, which is say 5 times 10 to the 6th kilograms. And it's actually 30.0 times 10 to the 3rd meters away. And now let's say dead center between that forms an equilateral triangle. And right here is going to be a mass M3, which is equal to 6 times 10 to the 6th kilograms. And this is 30 meters, 30 times 10 to the 3rd meters. And this is 30.0 times 10 to the 3rd meters. Okay. What I want to know is, what is the net force on M3? Okay. So there's a couple ways you can do it. And the normal way we do it is we just compute the magnitude and then we make it a vector by thinking about the geometry of the system. Does anybody know anything about the geometry of this particular triangle? Know what it's called or anything like that?
It's an equilateral triangle.
Equilateral triangle. That means all three sides are equal, and that means all three opposite angles must be equal. But we also know that the three angles inside of a triangle has to add to give you, anybody recall?
180.
Yes. So if you divide 180 by 3, you get 60, 60, and 60. Okay. So that's going to help us. Now, first thing I want to look at is sort of like a free body diagram for M3. So here's M3. There's X. There's Y. I have a force acting on it. Notice this angle right here is only half the angle, so that one's going to be 30 degrees. But I have a force acting on it, pulling it this way. And that's F1, 3. Actually, I should write it the other way. When we do this, we normally say the force on the first guy. So in principle, I should do something like this. Force on 3 due to 1. Should be that. That should be what I call it. Okay. And it should point this way. Anybody know why it points down and to the left instead of up and to the right? Anyone? I'll give you a hint. Scarlett Johansson or Channing Tatum or Butterbean the boxer. Okay, that was a joke. Okay, it's attractive. The force is attractive, right? So that means M3, if left to its own devices, would move towards M1 as a result of M1. We're ignoring M2 completely right now, but that's why it points down and to the left. It's got, as Newton said, it's got a point along the line connecting the center of masses. These two things we're treating like point particles. It's got a point from one center of mass to the other, but it's attractive. So that means M1 is pulling M3 towards it. Does that make sense? Now, the other part of this is the force, which we'll call F32. Now, I drew that down and to the right. Does that seem right, or should it be up and to the left? Anyone? Bueller?
That seems right.
Yeah, it should be down and to the right because it's again attractive. So first off, let's calculate F31. We know that's 6.67 times 10 to the negative 11th, leaving off the units right now because I'm trying to fit it in the space. We've already seen how the units work out though, so that should be fine. What we have here is basically 4 and 6. So I'll say 4 times 6 times 10 to the 10 to the 5th. That did not look good. 10 to the 5th times 10 to the 6th. And I think you can see why I did that, because 10 to the 5th times 10 to the 6th is 10 to the 11th, right? And then I'm going to divide it by 3.0 times 10 to the 4th squared. Clearly that was the units of G are going to cancel out with the units of the two masses and the distance squared and just give me newtons. So that's fine. The 4 times 6 is going to be 24. So I'm going to get 24 times 6.67. Notice the 10 to the 5th and 10 to the 6th cancel each other out. So I'm going to get 6.67 times 4 times 6, which I told you was 24 already. That gives me 160.08. And now I'm going to do divided by 30 exponent at third, and I'm going to square that sucker. and that gives me 1.778. So I'm gonna call that 1.78. I'll go ahead and write 4 sig figs, 7, 7, and that 8 rounds to 9. 1.779 times 10 to the negative 7th newtons. Okay. Now, how do we deal with that? Well, what we have here is 1.779 times 10 to the negative 7th newtons acting at 30 degrees like this. So you notice that is that angle, that side next to the 30 degree is actually adjacent to it. One's the hypotenuse and the other one is adjacent. So we know this one is involved with cosine. So we'll say f sub y is going to equal negative, because it's pointing in the negative y direction, f 3, 1 times the cosine of 30 degrees. And of course, remember our special triangle. We know that the 30 is opposite from the small side, which is the 1. So that means it's √3/2 or something like that. Okay. So I can go ahead and write that out. I'm going to take 1.779 times 10 to the negative 7 newtons negative, and multiply that by cosine 30 degrees. And I'm really ignoring sig figs here, so don't put too much stock in the sig figs. Just assume we got a buttload of them and I can put them anywhere I want. And that gives me negative 1.54 540 times 10 to the negative 7th newtons that way. And I think you can see that f sub x for this one also points in the negative direction. So I'm gonna have to put a negative there, and it's going to be f3,1. Notice that's the opposite side. So it'll be f3,1 times the sine of 30 degrees. Of course, the sine of 30 is 1/2. So we can automatically guess that it's going to be about, crap, that's not a very even number. So it's 1.78. So it'll be 0.5 plus, that'd be 0.85 plus 0.859. So about 0.859 times 10 to the negative 7th. Let's see what we get. I want to say negative, I'll pull this number again, times sine 30 degrees, and I get negative 8.89. And the next digit is 3 times 10 to the negative 8 newtons. Okay. So you see how we just took the magnitude formula and we took the diagram and made a direction for the vector, and then made that vector basically the hypotenuse of a triangle by basically drawing a x component and a y component that are obviously parallel to the x-axis and the y-axis. But you had to decide on the sign. That's the big deal, is you've got to always decide on the sign. So now we're going to do the same thing for f3,2, and f3,2 is equal to 6.67 times 10 to the negative 11 again. This time it's 4 times, whoa. Okay, so anybody notice that I did 4 and 6, not 6 and 5? Okay, that was right. Never mind. Cool. I thought I'd done it backwards, but no, I'm good. So f3,2 is supposed to be 6 and 5, not yeah, okay. So this is going to be 6 times 5 times 10 to the 6 times 10 to the 6 in this case. Notice the 3 and the M3 and M2 both have exponents of 10 to the 6th. And then that's going to be divided by 30.0 times 10 to the 3rd meters. And that's going to be squared. So I'm going to say 6.67 times 6 times 5. And then I'm going to divide that by 30 times 10 to the 3 squared. And that gives me 2.00 times 10 to the, I'll go ahead and call it 2.000 times 10 to the negative 1, 2, 3, 4, 5, 6 newtons. So in this case, this is supposed to be, again, 30 degrees. Clearly, I did not draw 30 degrees. This part right here is 2.000 times 10 to the 6 newtons. This part is F sub y, which is, again, negative 2.000 times 10 to the 6 newtons times cosine 30. Oh, that writing just got bad there. 30 degrees. And this side right here is positive. So I can say F sub x is positive 2.000 times 10 to the 6 newtons times the sine of 30 degrees. So when I do that, I'll say, I'm going to do the y one first. And this gives me, whoa, what just happened? Oh, okay. I don't know what just happened, but I definitely didn't get the right thing calculated. So I'm going to do.
Is there not supposed to be a -6?
Yeah. Oh, thank you. Yeah, you did get me on that. I'm glad you caught that. So yeah, it has to be a negative up there. It has to be a negative. I just noticed my calculator is only showing 1 sig fig. So really, these other digits were 2, 3, 2, 2, 3. So let me fix that real quick. I didn't realize. I thought it was flat 2. I was wondering how that got a flat 0 after the 2. So it's actually should be equals 2.223 times 10 to the negative 6. Okay, so that's got to be corrected in these guys. So 2.223. Boy, that is not pretty, but I think y'all can make it out. So I want to say that times cosine 30. And that gives me an equally small number. But again, it's probably, it's going 1, 2, 3, 4, 5, 6. It's giving me 2 point something times 10 to the negative 6. Let's try this. 2.223 times cosine 30. 1.9275. So let's rewrite this. Sorry, guys. My calculator is only showing 1 sig fig on there, and it's bothering me. And I don't have time to change it right quick because I'm using a calculator I'm not that familiar with. So 1.959257. 92517. So I'll call this 925 times 10 to the negative 6 newtons. Now with the other one, I'm going to say 2.223. That should just come out to be 1.112. But times cosine, or excuse me, times sine 30, because it's just 1/2. Yeah, this one should be 1.112 times 10. Actually, that's 1.111. Sorry, I rounded in the wrong place. 1.111 times 10 to the negative 6 newtons. Okay, so we now actually have the x component of F31 and we have the y component of F31. We have the x component of F32 and the y component of F32. All we got to do is add the x components, add the y components, and then we'll have the total force. So F total, I'm going to write it the simplest way, which is that IJK notation. So when I add the two x's, which notice that's negative 8.893 times 10 to the negative 8th, and then the other one is positive 1.111 times 10 to the negative 6. When I add those two, that actually becomes subtraction, but I'll just put that answer in front of I hat. So I'm going to say negative 8.893 e to the negative 8, and then add to that 1.111 e to the negative 6. Thank goodness your student, one of our students caught me on that. And that gives me 0.000001. And of course, my calculator is being a jerk, so I don't even know what's after that 1, but let's try 10 to the negative 8 would be, that's like 0.08 minus our negative 0.08 from 1.111. 1.111 minus 0.08. See, what I'm doing is I'm doing 1.111 minus 0.08, because the power of my the 8.893 is 10 to the negative 8. So if I wanted to make that 10 to the negative 6, I would multiply the 10 to the negative 8 by 10 to the 2, and that would mean I'd have to divide the 8.893 by 10 to the 2. That means the decimal moves 2 places to the left. So I can do it that way, and that'll actually show me what my digits are. So I'm just letting you know, because my calculator is doing the same stupid thing. So that's 1.031. So I'm going to say 1.0, and there's no negative on that, 1 times 10 to the negative 6 newtons I hat is the x component and with its I hat vector. And then the j hat vector, okay, that's going to be the f sub y, which is negative 1.540. So negative 1.540 e to the negative 7 plus, now I'm going to take the y component of the other one, which is negative 1.925 e to the negative 6. And again, it's giving me the same stupid thing, but the 1.54 times 10 to the negative 7th, I can make that negative 0.154. So negative 0.154 plus negative 1.925. That should give me 2.079 negative. So this is going to be minus 2.079 times 10 to the negative 6th newtons in the j hat direction. So does everybody follow what we did there? I'm still not finished. I need to write that in a magnitude and direction form, I think, just to make sure y'all guys know how to do that. And hopefully that'll help you a little bit. But let me recap for a second, just to let everybody know what we did. So we were asked to find the total force on M3. We see that there's two other masses that are applying a gravitational force to M3, M1 and M2. So if we take the force that M1 is applying to M3 and the force that M2 is applying to M3, we just had to add them. But they're vectors, so you can't just, randomly add numbers like they're vectors or vectors like they're numbers. So what we first did was calculate the force of attraction between 3 and 1, and notice that the the force on 3 due to 1 would point diagonally down and to the left, parallel to that side of the equilateral triangle. So I calculate that magnitude. Then I use trig functions to find the x components and the y components. And I made note of the sign. Notice you have to instill the sign yourself. You've got to actually choose what the sign is going to be for those components, because you're always just going to choose the easiest angle to deal with. So you can't just randomly say if the angles between 0 and 90, x and y are both positive, like you did in trig. So that's why we chose those signs and forced them. And then when we did F32, we realized that one would point down and to the right. Well, the right was a positive direction, so we got a positive x component, but a negative y component. So we again just use trig to sort out that mess. And now we're going to take that 1.031 and 2.079, dang, I already forgot it. 1.031 times 10 to the negative 6 newtons in the I hat direction, minus the other one was 2.079. I think I can make a 9 this way. Why not? Times 10 to the negative 6 newtons j hat. That's what the vector looks like. Now they're both 10 to the negative 6, so I can play around with the what's called the mantissa, the number that's in front of the x. I can play with that instead of having to deal with the whole number. And you'd see that clearly the clearly the y component is markedly larger than the x component. That's because the two y components helped each other, and the two x components, in fact, fought each other. So if I put an xy coordinate system like this in here, then what I would do is I'd represent the x coordinate or the x component as positive, and maybe I'd say it's 2 squares long. And I'd say that's 1.031 times 10 to the negative 6 newtons. Notice I just paid attention to the 1.031 to say it's going to be roughly half as big. And then I go down 1, 2, 3, 4. That shows me roughly the size that I expect, and that is 2.079 times 10 to the negative 6 newtons that way. And that means, in fact, our resultant vector is this guy. So what I'd like to do is put that in magnitude and direction format. Can anybody tell me how I might get the magnitude of this vector?
Don't you take like the square root of the square of each of the components?
Exactly, because they're perpendicular to one another. Pythagorean theorem works. So yes, the magnitude of F total, which I'll write like this, is equal to the square root of, let's just say 1.031 squared plus 2.079 squared. And all that'll be times 10 to the negative 6 newtons, because it really doesn't matter. You're going to do that anyways, right? So I'm going to do 1.031 squared plus 2.079 squared. I got 5.382. Now I got to take the square root of that. So working on it. That gives me 2.321 times 10 to the negative 6 newtons. Okay, so that's the magnitude. How about the direction? What do you think we could do? Let's say we call this the direction.
Wouldn't it be like tangent y over x? So it'd be like tangent j over I.
Yep. So phi And notice how I've drawn it on the diagram. Since I've drawn it like this on the diagram, if I'm the student, I don't have to do anything else for the instructor. I'm just going to give them magnitude and direction, and he'll know exactly what I mean. If you didn't show this, then it'd be hard to say. You'd have to call this a negative angle. You could say 2.321 times 10 to the negative 6 newtons at negative 64 degrees or whatever it is. We'll find out in a second though. So it's the inverse tangent of, notice I'm eliminating the sign. So I'm just going to say 2.079. That's the y component over 1.031. Notice I also got rid of the 10 to the negative 6 because I really didn't need to, because the 10 to the negative 6 is going to cancel out anyways. So I'll take my trig function, inverse tangent. Whoa, I hate this calculator. It's such a pain in the butt. It's slow, and then you go to click on something and you realize it hasn't moved yet. So you hit it again, then you hit it twice, and it's back where it started from. And I just want to punch a baby. 2.079 divided by 1.031. I hope y'all know this is my sense of humor. I'm not really that macabre. Oh, that was pretty close. I said 64 degrees at 63.6. So 63.62 degrees. And again, I just ran roughshod all over the units here. I mean, all over the sig figs here. So that's okay. It's not a big deal. I just ran roughshod over them. And we know that the significant figures isn't the best way to deal with numbers anyways. So keep that in mind. But if you're doing it with the homework system, they're expecting you to use the sig figs, and they treat numbers like 5,000 as ambiguous. Whereas I teach in my lab that 5,000 has 1 sig fig, but 5,000 followed by a decimal point has 4 sig figs. So we can say finally that F total is equal to 2.321 times 10 to the negative 6 newtons at, and if I didn't even have the diagram, I could just write this and everybody would understand what I mean. And that's 63.62 degrees negative. Because if you measure counterclockwise, or excuse me, if you measure clockwise, in other words, downward from the positive x-axis, that's understood to be a negative angle. If you measure counterclockwise from the positive x-axis, that's understood to be the standard angle, and it's a positive. So we do rely somewhat on what everybody's learned in math to make sense of all this. Anybody have any questions on that? Did anybody verify any of my calculations as we were going along? Okay. Normally what you want to do is you try to want to at least push in the same buttons in your calculator when I get to that part, because obviously we're recording all this in video form and in note form, so you're not going to miss anything. But that just helps me, because there's always a chance that my fat old fingers, you know, the ones that don't recognize the end of the pencils off, but my fat old fingers might actually just hit a wrong button and give you a wrong answer. And later when you're trying to study, you might say, I don't get this answer at all. How did you get that? And I don't want y'all going through that kind of stress. So try to give it a try as we go on. Any questions?
No, I don't have a question, but your answer is right though.
Okay, thank you. Appreciate that. I knew some of you were. It's just, yeah, most people don't talk too much. So I'm going to do something else kind of neat now, and I'm going to take a sort of weird approach, but I'm going to pretend like the planets are in fact orbiting our sun in perfect circles. Now, it turns out if you actually do the full derivation correctly, where it's not in perfect circles, it is in ellipses like Kepler said, and you work out the details of all that, you still get the same result. So that's a good thing. But it's easier to work out this way, and you get the right result. So I'm going to go ahead and do that now. So what Newton was able to pull off was he was able to give us a formula for gravity. And prior to Newton, we had sort of the Ptolemaic model, and the Ptolemaic model was really super weird. So in the Ptolemaic model, they started off in ancient Greece thinking, well, they actually considered the Earth being the center, and then they considered the sun being the center. A lot of people don't realize that, but the ancient Greeks did actually consider the idea of the sun being the center of our solar system. Of course, when we say solar system, they would interpret our solar system plus the 7 to 10,000 stars we see throughout the year as the entire universe. They didn't realize there was anything beyond those stars, and they're not seeing any galaxies. They don't see the stars in galaxies. We didn't even know that there were other galaxies until around somewhere between 1905 and 1911. I can't remember, is when Hubble first observed the Andromeda galaxy and saw that it was shifting. So initially, they sort of felt like we were the center, but someone, Anaxagoras, I believe was his name, he postulated that the sun was at the center. Now, the reasoning goes, if the sun was at the center, then the Earth is actually moving back and forth in space around the sun. If you do that, then what you would expect to see is a star that's really close to you. When you're looking this way at it, let's say this is a star. Actually, let me stop sharing my screen for a split second. Whoa, no, where I am. There I am. Okay. So let's imagine my eye right here is, say, the Earth in January, and then my other eye, over here, is the Earth in June. Okay, about 6 months apart. And let's say this is a nearby star, and that screen way out there in front of me is not a nearby star. So when I look through my left eye, I look and I see this star, and I see this list of names in the background. But then when I switch and look through my right eye, I see the star with the image of my violin back there behind the star. Okay, so what that looks like to me is my star went back and forth between here and here, and that's called parallax. The nearer the star is, the more it would appear to move, and the farther the star is, like if it's way out here, it would barely move. Or if it's way out here, it would barely move at all. And if it's really even farther, you might not even see it move. So that was what they were looking for. So they said, hey, if the sun's the center, then clearly we should see some parallax. And they actually looked, and they just didn't have telescopes and stuff at that time. They had really good eyesight, and they had really dark nights because, no electricity, right? So they had great viewing, but no telescopes. And they couldn't detect with all their measurements, which they actually had some pretty good measurements in that time. You remember how good the pyramids were, and it goes Egypt, Greece, and Rome. So Egypt preceded Greece to some extent. So Egypt, Greece, and Rome tells you that Egypt was created beforehand, and they have, of course, the pyramids, which were done pretty well geometrically. So they had good measurements, but they still couldn't detect any parallax. So they threw that idea away. The sun-centered or heliocentric universe was thrown away. So that left them with the Earth-centered universe. And that's all well and good, but the Earth-centered universe, of course, turns out it's completely wrong, which, that's a little bit of a problem. But they didn't know that. And what they were doing is they were observing from one time to the next, and they had made certain observations since that initial time, and it got quite complicated because they didn't understand exactly what was going on. So they ended up having to piecemeal fix it. So how did they fix it? Well, they said, okay, well, let's imagine the Earth is right here at the center. Okay. And they said, okay, the moon is orbiting around it. That's fine. We just see the moon progressing. In fact, it moves about 1 moon diameter every hour. And we can trace that throughout the day. It moves backwards to the motion that it rises and sets and stuff like that. So you can keep track of that. But then the next thing out was weird. They had Mercury, which stayed really, really close to the sun. So they couldn't make any sense of that. But also, Mercury sometimes went the same direction as of the sun and went faster. Other times it went the opposite direction of the sun and went slower and stuff like that. So the only way they could account for that is they had to imagine an imaginary line going from the center of the Earth to the center of the sun and to the center of the orbit of Mercury. So let's say this is the orbit of Mercury and this is the sun. So the sun was making this giant circular orbit, but Mercury, well, that looks bad, but Mercury was on a smaller orbit right here, and it would go around this way like this, but the center of that smaller orbit stayed on that imaginary line. And then Venus, which actually could go quite a bit farther away than Mercury could, Venus was on a similar circle, but the circle obviously had to be bigger. And I'm drawing it as an oval, but it really was supposed to be a circle. So this is Venus right here. This center is called this orbit right here. This is called a deferent, and then this thing's called an epicycle. And the same thing here. This is a deferent, and the smaller one's an epicycle. And what that allowed for them to do is understand how, in fact, Mercury and Venus went different directions relative to the sun. But then they got to looking more, and they discovered that sometimes, well, basically all the time, you look at a star, and the stars sort of don't keep up with the sun. So the sun's rising in the east, sitting in the west, but it's moving sort of in the opposite direction against the background stars. Well, the planets are normally moving that same direction too, but then every now and then they get bright and flip around the other way. It's called retrograde motion. So they couldn't make any sense out of that. So they ended up having to make epicycles and deferents for Mars as well. Only those were not connected to any kind of imaginary line connecting the center of the sun or anything like that. So you had Mars, and then you had Jupiter, and then you had Saturn, and they were all the same thing. That became the Ptolemaic model, named after Ptolemy. So this actually started a long time before Ptolemy was born, and continued for a long time after Ptolemy was dead, being the model. And in fact, Aristotle latched onto it. And by the time we get to, let's say, Copernicus, the church has completely interpreted all of Aristotle's teachings in terms of the Bible, or excuse me, interpreted all the Bible in terms of Aristotle's teaching. So it was really ingrained that you didn't really want to mess with it because a lot of problems might arise. But Copernicus was an astronomer, just like Galileo was, just like Brahe was. And these people would get paid by their king basically for creating annals, are sort of big books. And these big books, almanacs, if you will, would tell them what constellation a given planet will be in at a given date in the year. And it'll work out for maybe 10 years in advance. That's part of how they made their money. Of course, back then they didn't realize horoscopes and that kind of stuff were a pseudoscience. They're not a real science. They're a science that actually, it's very normal for you to find several, let's say, astrologists, we'll say several different astrologers. They can all interpret exactly the same occurrence different ways. That's sort of a hallmark of a pseudoscience, right? So that's part of the reason why it's not a pseudoscience. And you can do various experiments and show that it doesn't do very well predictively. I've done some good ones in my astronomy class. But at the time, they didn't realize that. They didn't really have a scientific revolution yet. They didn't understand the importance of independent observations. They didn't understand the importance of testing for incorrectness as opposed for testing for correctness, and a lot of stuff like that. And they really believed in appealing to higher authorities, which is what Aristotle was. But by the time Copernicus comes along, this circle on circles became so complicated. It became so complicated, in fact, that the Earth wasn't even at the center. The Earth was off center, and then there was another point called the equant point, where if you watch the planets from that point, then they appeared to move in uniform motion as opposed to speeding up and speeding down. Because one of Aristotle's premises was that the heavens are perfect, therefore they're unchangeable. So for instance, if a planet is going one particular direction, it always has to go that particular direction, period. If it didn't, then it either went from incorrect to correct, or it went from correct to incorrect, both of which are having incorrect at some point. So that's not acceptable. So that was how all this model was made up. Copernicus comes along and is like, we've lost our way. And this is why I don't call it the Copernican revolution when I talk about the scientific revolution. Copernicus said, we've lost our way. Aristotle taught us that the heavens were perfect. The perfect shape is, of course, a sphere. If you have to do it in 2 dimensions, of course, that would be a circle. And we've gone way astray from that. We've got epicycles and difference and equipoints. He said, I can remove all that extraneous crap by just making the assumption that the sun is at the center. So when he did that, when he made the assumption that the sun was at the center, he got a simpler model. And in fact, he got a model that made more sense, because with the sun at the center, there was a very good reason for Mercury to have the shortest period. And that's because it was closest to the sun. And then Venus, of course, was farther out. And of course, that explained why it could go further away from the sun. And then outside of that, of course, is the Earth. And the moon orbited it. And then outside of that was actually an asteroid belt. But after that was Mars. And then Jupiter. And then Saturn. And that's all they knew about. And in fact, that's why we have 7 days of the week. If you trace back the origins and the etymology of our words, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, those are the heavenly bodies. You can see obviously that Sunday is for sun and that Monday is for moon. Tuesday's a little harder. You have to go through a couple different languages, but ultimately you figure out that's Mars, or maybe it was Wednesday was Mars. Thursday is Thursday, which is essentially Jupiter. Friday is another one. But basically the reason we have a 7-day week is because of these heavenly bodies. All right. Now this is what Copernicus did, but everything was still a circle. These were all perfect circles. And it made some sense, but it was really no better than the Ptolemaic model. In other words, it was just as error prone and just as likely to be out of whack 10 years down the road. And Kepler comes along and has a whole different idea. Kepler has an idea that it's not a coincidence that Mercury, Venus, Earth, Mars, Jupiter, and Saturn is exactly the right number of planets to have if the planets were separated by the perfect bodies, the perfect solids. So they had this idea in geometry that there's 5 perfect solids, and I think it's 5. Anyways, he imagined that maybe that was what was separating the crystalline spheres. So they imagined the planets were actually not in circular orbits. They were sort of embedded in a crystalline sphere. And the biggest, most crystalline sphere was basically a crystalline sphere with little holes in it that could show you the fire that was outside of that crystalline sphere. And that's why the stars blinked, was because the star's light was blinking through there like flames looking through a hole. So when you're looking through a hole at flames, you'd see them blink. So that was sort of their idea of what the stars were. They were just holes in the giant crystalline sphere. All the other planets were in crystalline spheres, and they, of course, moved while the crystalline sphere rotated. So that was the big idea that they were going for. And Kepler had a different idea. He imagined those crystalline spheres were separated by the perfect solids, and he wrote it up and worked it out a little bit mathematically and sent it to all his friends. One of his friends was by a guy by the name of, we spell it Tycho. I think it's pronounced Tycho Brahe. He's a Dane, same place that, for instance, Niels Bohr was from. And he's an interesting character in history in that he was very arrogant. He was noble, meaning he had royal blood. And he was very good at convincing people that he was the smartest person in the world and that they should give him money. And in fact, while he was in college, he got in a duel one day over who was the better mathematician and got his nose cut off. So he literally had his nose cut off and then wore a prosthetic made of brass and silver and gold that he stuck on his face with wax. And he was a bit of a Russell Brand. Y'all know of Get Him to the Greek, or Forgetting Sarah Marshall, or any of those movies. So that's Russell Brand. And that's sort of the character that Tycho Brahe is. And Russell Brand's not smart and not dumb by any stretch of the imagination. He acts like a dumb person, but he's actually quite intelligent. Either way, Brahe was the same thing, and he was a party animal. Like, he would get up in the morning and drink beer and have parties all day. And then the party would close up midnight or so, and he'd go out and do observations. And without a telescope, he could make measurements probably as precise as maybe a first-year grad student makes with our modern technology. He was using just basically a huge protractor mounted in such a way that he could read very precise angles through a hole in an opposite wall and something like that. And he had his own idea. His idea, check this out, this is crazy. His idea was that the Earth was here and Mercury orbited it, and Venus and Mars and Jupiter and Saturn, all of those orbited it. But here's the crazy thing. The sun was right here and the Earth orbited the sun. So that was crazy Tycho's model. And he discovered he wasn't as good a mathematician as he'd like to be. So when he gets this letter from Kepler about having this wonderful model worked out, he offers him a job. Now, Kepler is the Mike Pence of physics. And I don't mean that in a bad way against Mike Pence. I mean it in the best possible way. He was an ultra conservative Christian. He was a strong member of the church. A poor guy, he had a mom that he kept having to get out of prison because he kept arresting her for being a witch and going to kill her because she was an old lady. And when old lady, you don't have no teeth, the men tend to think of her as gross and icky. So they keep accusing her of being a witch. And he literally on multiple occasions had to go and defend her as not a witch. He was also trained in medicine, but he was a really unhealthy little critter. He had rickets and piles and shingles and all sorts of crazy stuff wrong with him. He was nearsighted, so he couldn't be a really good astronomer anyways, but he loved astronomy and he studied it, but he was straight laced, like not drink a drop, not smoke, not any, and I don't even know if they had smoking back then. I'm just saying he was really prim and proper. So you can imagine Mike Pence moving in with Russell Brand would probably not be the coolest thing. And it didn't go very well. In fact, it seemed that Tycho Brahe realized how brilliant Kepler was and was keeping him from getting as much data as he really wanted to do his analysis. And Kepler was getting quite upset because he saw him as a brilliant man with excellent experimental technique, so much that he literally trusted his data well enough to throw out the Keplerian model, to throw out the Copernican model for his own model, all because of his respect for Brahe as a scientist. So he had all this, negative stuff going on, and Brahe was upset because he didn't want his legacy to be forgotten. And as you can tell, most people have never heard of Brahe, but they have heard of Kepler, and that's exactly what happened. But as would have it, Tycho Brahe, I don't know if you realize this, but noble people are so good that they don't pee or poop at all, clearly, right? So that was sort of the impression that nobility like Tycho Brahe would want to give to people. So he would party all day, and he would never let himself go to relieve himself because that would give them a tip into seeing that he actually had to go to the bathroom. So one day he did it for so long that his bladder exploded, and he died a horribly painful septic death of basically a busted bladder. And stories were originally told that that Kepler broke in and stole his stuff. We're not really sure that that's the case, but what we do know is Brahe's family tried to stop Kepler from getting the data, and he won the right to get the data in court. So Kepler took it and actually dedicated his book when he finally wrote it. He dedicated it to Brahe, showing that he really had a great deal of respect for how good of a scientist Brahe was. And what he had done was basically worked out a whole new model that was closer to the Copernican model. He had to throw out the Brahe model. He had to throw out his own model of the perfect solids. And what he came up with was Kepler's laws of motion. So that's what I'm going to talk about now. So Kepler's laws of planetary motion. Okay, his first law. The planets orbit in elliptical orbits around the sun which is found at one focal point. So the scenario here is if you nailed a nail on a piece of plywood, and then you tied a string to the nail and tied another string to a pencil, and then you held the pencil perfectly vertical and made sure the string stayed perfectly taut, you would trace out a circle. Does that make sense to everybody? That's the definition of a circle, right? All the points that are equidistant from a single point, that single point being the center. Well, with an ellipse, what you do is you take two nails and you connect them with a piece of string that is in fact longer than the distance between them. So let's say one string goes from here all the way back down to here. And again, you pull it taut with your pen or pencil and run it around and you get this shape, which you should have already learned about the equation for an ellipse or whatever. And he was very specific. He said elliptical, not oval. He said it was an elliptical orbit with the sun at one focal point. Well, where the nails are the foci, which is plural for focal point. Okay, so what he's saying is the planets are not in circular orbits, which would have drove Copernicus to roll over in his grave, would have made Aristotle roll over in his grave, because an ellipse is really a bastardized version of a circle. But it turns out he's exactly right. In fact, the least elliptical orbit we have is Pluto's, and Pluto's not even considered a planet anymore. And if you actually drew a circle and Pluto's orbit to the same scale right next to one another, it would take you a little bit of measurement to figure out which one is the circle and which one is the ellipse. So it's really impressive that without telescopes, the data that Brahe had was good enough for Kepler, and Kepler was that good of a mathematician to figure out that, in fact, it was an ellipse, not an oval and not a circle. So that's one of the major things. It turns out when Newton came up with his law of gravity, he actually proved a more general law that basically said the only types of forces that can give you closed orbits, meaning orbit where you run back over your path, so you repeat yourself over and over, was an F over r squared force, or an F is proportional to r force. So Newton was able to prove mathematically that those two forces are the only forces that can make stable orbits. And in fact, that the orbits they make were conic sections. Okay, so this is what Newton had found. So in fact, we can say Kepler's first law is a result of the 1 over r squared force. And the conic section, by the way, is you imagine two of those cheap little cone-shaped cups that you see at car dealerships. So imagine two of those tail to tail like this. And of course, imagine them going on for infinity in both directions. If you slice that parallel to the axis, then you'll get something that looks like a loop on one side and a loop on the other side. That's a hyperbola. If you slice it parallel to one of the sides, then you'll get a shape like this, and that's called a parabola. Those two are not closed orbits, okay? But if you slice it perpendicular to the axis, then you get a circle. And if you slice it between perpendicular to the axis and parallel to the side, then you'll get an actual ellipse. So you can see a circle here and an ellipse here. Those are the conic sections. Okay. Kepler's second law. The planets. Whoa, that wasn't good. The planets sweep out equal areas in equal time. Okay, what does that mean? Well, if you imagine the elliptical orbit going like this, sorry about that little divot over there, and this being your sun, whoa, I just erased that and don't even know how I did it. But anyways, this being your sun, if you imagine the sun goes from here to here in 30 days, then the area inside of there, anytime you create that area with the planet's orbit, then that's going to take 30 days. Well, you can see down here on the left side of this orbit, it's sort of like a pizza slice, but the pizza slice is really long on the right-hand side, but on the left-hand side, it's really short. So if this area and that area over there were equal, then this would also take 30 days. That's Kepler's second law. And it turns out that's due to conservation of angular momentum, which Newton was also able to show. And then Kepler's third law, the square of the period of an orbit is proportional to the cube of its semi-major axis. I notice I left out a bunch of stuff in this. I don't know how I did it, but I did. So the square of the period is proportional to the cube of the semi-major axis. And in fact, what that means is T, if you use T for the period, is directly proportional to, let's say, A for the semi-major axis cubed. Now, if you take the case of the Earth, then you have 1 year squared is equal to 1 astronomical unit, which is the distance between the Earth and the sun on average, basically, cubed. Then you realize the constant of proportionality, if you use units of years and astronomical units, is just 1. So that's a nice way of doing it. You don't have to, as long as you use years for the period and astronomical units for the semi-major axis, then it's just T squared equals A cubed. So that's kind of nice. But I need to explain to you that we can sort of code that and call that semi-major axis. We can say the average distance between a planet and its star is 12 astronomical units. What is its period? That's a sneaky way of us trying to make sure you understand what semi-major axis is and testing you on Kepler's third law. So let me explain to you what the semi-major axis is. So if we draw the ellipse like so, this is the major axis. That's both a thing and a distance. This is the minor axis, also a thing and a distance. I think you can guess that this little part right here is the semi-major axis. So is this part, the other part on the other side. Okay, so if you think about it, remember the sun would be, say, here. And if you take this little distance right here, this distance is the perihelion distance. And this distance right here, let's do this one blue. That distance is the aphelion. Okay, you can see the aphelion is the farthest the planet ever gets away from the sun, and the perihelion is the nearest. So if you took the sum of the farthest and the nearest, what would those two distances add to give you? Remember, all these terms are things and distances. So if you add the perihelion distance and the aphelion distance, what distance will you get? Come on, y'all can see that on there. Nora, I bet you know.
Just the major axis?
Yes, it's the major axis. The major axis, which we can say is 2 times A, of course, that's got to equal the perihelion plus the aphelion. Okay, so what that tells you is, in some sense, A is the average distance. So that's why occasionally we can get away with telling the student that the average distance between the planet and the star is 15 astronomical units. And then you're supposed to be able to say, oh, okay, well, I think they mean that's the semi-major axis. Okay. Any questions on that? All right, so this actually gives you some equations you can solve, but it also tells you stuff like, for instance, that the fact that I told you the angular momentum is conserved, that will later allow us to do things like, if I tell you the velocity of the planet at perihelion, then you take the mass of the planet, multiply it by the velocity at that point and the distance away at that point. That's going to be the same thing as the mass of the planet times the velocity of the planet when it's at aphelion times the distance it is at aphelion. So that's one of the kind of things you can do. But the other thing you can do is just use that equation, t squared equals a cubed. Now, let me show you the derivation that I was warning you about. So we know that Newton's law of gravity says that the force of gravity is equal to g m1 m2 over r squared. We can imagine that the sun's mass, which is normally drawn by this, I think y'all can see why, is much, 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 much greater than the mass of any planet. In fact, 99.9% of the M of the solar system is actually equal to the mass of the sun. So yeah, the vast majority of the mass is in the sun. In fact, the Earth it would take 300,000 Earths to make the weight of the sun. So it's really, really freaking huge. It's 105 Earth diameters tall, but it's like a third of a million times heavier than the Earth. So that's really, really big. So that suggests if I put a planet out here, the sun's not going to move. It's sort of like me holding the end of a leash while my little chihuahua tries to run around. He's not going to pull me very far because he's only like 4 pounds. So let's imagine a circular orbit that was just drawn really badly. But anyways, I know there's a way I can do it better. I'm choosing not to. Let's say that is the distance r. Actually, let's go ahead and use the letter that I want to use, which is the letter A. Okay, because that's going to play the role of semi-major axis later on anyways. So I'm going to use that. Now, in order for this mass, little m, and that mass, big M, in order for that to be in a circle, a circular orbit, then we know the acceleration of the little mass m has got to be v squared over r, or excuse me, v squared over a. So using Newton's second law, the summation of forces equals mass times acceleration is going to give us g times the mass of the sun times the mass of the earth. By the way, this is the symbol for the earth. Now I'm doing this for any planet, but I just thought I'd show you what the mass of the earth is supposed to be represented by. Over a squared has got to equal the mass of the earth, because that's the one that's got to be accelerated, times v squared over a. So you can automatically see that the masses are going to cancel out. You can also see that one of the a's is going to cancel out. So we now have g, mass of the sun, over a is just equal to v squared, but v is actually equal to 2 pi times a over t. Everybody recognize what 2 pi a is?
Circumference.
Yeah, that's the circumference. So if you divide the circumference by the period, you get the velocity, right? So now I have a formula for the velocity relating the radius and the period to g, m, and a. So now I can go ahead and work this out. I'm going to get, let's see, g, m, that g turned out ugly. So I can say g, m times t squared is equal to, notice I pulled the t from the bottom over here, it's squared. It's going to be equal to 4 pi squared a cubed. It's a squared here, and then I took the a from the bottom and put it over there. So what we can say is that t squared is actually equal to 4 pi squared over g m sun times a cubed. We've just derived Kepler's third law. Okay, now again, I did that for a circle, for a circular orbit. It turns out if you do it, one, not assuming the sun is so darn big, and two, not assuming a circular orbit, assuming a elliptical orbit, you get a more general expression. But the difference is in the bottom, you'll have g times the mass of the sun plus the mass of the planet down in the bottom. And you actually use the semi-major axis as opposed to the radius, which is really what we were using. So you don't need, I mean, you'll need to know that that's what it really looks like if you have two comparable mass planets orbiting one another. What they then do is orbit the common center of mass of the two. So this is what you get otherwise. Whoa, Nelly. Anybody have any questions on that? All right, so that's another type of problem you can solve. You can do really simple things, like for instance, if I take and say the semi-major axis, let's say the period of a planet is in fact, let's say we found a new planet. Orbiting our sun, and its period is t equals 1,000 years. What is its semi-major axis? In other words, what's its average distance from the sun, say? Okay. So this is nice. We know that t squared is equal to 4 pi squared over g times the mass of the sun times a cubed, but using years and AUs, it comes to t squared is just equal to a cubed. In fact, that if you put this 4 pi squared g over gm in the units of, it would actually have to be units of seconds squared per astronomical unit cubed. If you do that conversion, you'll get exactly 1. Okay, so we could use that. We can say, okay, well, t squared is equal to a cubed tells me that 1,000 squared is equal to a cubed, and 1,000 squared, of course, is 1 million, and that's equal to a cubed. And of course, you probably can guess this already. Hopefully you can, but if you can, it's not a big deal. To solve equations with exponents in it, you can take the natural log or even the base 10 logarithm of both sides. And what happens is, actually, let's do log here, because log is really nice when you're doing powers of 10. So I'm going to say, whoa, I'm going to just erase everything evidently. Actually, let me go ahead and kill that so I can erase it a little further. So I'm going to say is equal to a cubed, and I'm going to do the base 10 of the logarithms. Okay, now the log base 10 of 1 million is in fact 6, because that's the power of 10. This is 10 to the 6, and it just becomes 10 times the log of 10, and the log of 10 is just 1. This becomes 3 times log of a, which you can get rid of by raising both sides to the 10 power. So now I get 10 to the 6 is equal to 3. Whoa, is equal to 10 to the 3 log a, if you want it like that. When you, and now this is a point where you can actually use a calculator, but basically what you'd end up getting is that a has to be 100. And you can test that yourself. A cubed would be 100 times 100 times 100, which would be 10 to the 6. So the answer is 100 astronomical units. Any questions on that? So you didn't have to do this part. In fact, I could have just left it. When I took the log of that, I got 6 equals 3 log a. So I could have said 6 divided by 3 equals the log of a. And of course, this is 2 equals log a. So that means a must be 100. because when you take the log base 10, that's y equals log base b of x implies x equals b to the y. So comparing these two expressions to this expression, you can see that 2 equals log base 10 of a means a is equal to 10 to the 2.
I have a
So,
question.
yes.
Couldn't you just take the cube root of both sides?
Yes, that's another way you can do it as well. Yep.
Okay.
In fact, that's a much easier way, and I was excited about showing you logarithms, and I think that's why I ended up doing it that way, because we never
I was
use
just
logarithms in
wondering if there
astronomy.
was. Yeah, I was just wondering if there was an advantage to doing that
No.
particular way.
No,
Okay.
some people don't know how to access a cube root as opposed to a square root, but I think all of you guys, since y'all finished calculus, y'all definitely know how to do all that.
Okay, thanks.
No problem. Any questions on that other than that? Any other questions, I should say? All right, so there's one more sort of part that I want to show you about this. And you should be able to use both versions of Kepler's third law, the one with the 4 pi squared over GM for the sun. And remember, if it's a different solar system, if they give you the mass of the new star, that's what goes down there. It's not the mass of our sun. Okay. And you can look up our sun. Its mass is 1.99 times 10 to the 30th. It's a huge mass. Earth is like 10 to the 27th, or 10 to the 25th, I think. Anyways, moon is like 10 to the 26th second or something like that. You can look up those are in the front cover of your textbook. But there's another thing, and that's called, well, no, I can't show it to you yet because we haven't studied. Yeah, we haven't studied kinetic and potential energy yet. So I'm not going to show you that, but there's a potential energy formula that comes from this law of gravity that we'll show you later. And that is kind of neat in that if you set the potential energy equal to the kinetic energy needed to escape the planet, you end up getting a formula for the radius that's exactly the formula we use in general relativity for the radius, in some sense, of a black hole. So it's one of the few instances where Newton's law of gravity gives you the exact same result that Einstein's general relativity gives you. But there's a way you can do it. And thank you for mentioning that. I completely forgot to mention you could just take a third root. You square that and you just take the third root of a. You could also do it the way I said here, which I don't know. I just got excited. I was thinking about logarithms when I was talking to you, and I didn't get to plan my lecture today. That's a little bit of what happened anyways. So let me show you this other thing that isn't the potential energy. So another way you could actually think about finding the force is you could make a vector. So for instance, we had before a mass here at 0, 0. We had a mass here at 0, 30 times 10 to the third. Excuse me, that was actually 30 times 10 to the third 0. So this one was 30 times 10 to the third meters, 0. And then over here, we had basically, since this angle right here is 60 degrees, then this distance right here would be 30 times 10 to the 6 meters times the sine of 60 degrees. If we remember our 3, 4, 5 our 30, 60, 90 triangle, the 60 triangle, the 60 degree is opposite the square root of 3. The 1 is down here and the 2 is here. So sine of 60 is root 3 over 2. So, which is about 0.707. So that's what gives you that. So I could say, I'm going to go ahead and do this number. That means this one right here, this mass, has a very specific coordinate. And that coordinate is 15 times 10 to the third meters. And then the y one, of course, is 30 e to the 3 times sine 60 degrees. And that gives me 2.59 times 10 to the 4, or 25.9 times 10 to the 3. I could add an 8 there if you wanted, but that's close enough. Okay. So if you really wanted to work this out without having to do the weird way I did the vectors, which actually I don't consider that weird, but some people might not feel that comfortable doing it. You can create a vector from here to here, or you can create, like we want, a vector from here to here, because that's the direction the force is, right? All you have to do is say, let's call this vector A. We'd say A is equal to, now we take 0, 0 minus 15 times 10 to the third meters, 25.98 times 10 to the third meters. And we actually write it like this: negative 15 times 10 to the third meters, negative 25.98 times 10 to the third meters. That's another way of computing that vector. Okay. Now, if we just took F equals G M1 M2 over R squared and multiplied it by that vector, we'd be off by the magnitude of that vector. So we don't want that. So what we can do is we can make a unit vector, A hat, which is just A divided by the magnitude of A. So if we take the time to compute the magnitude of A, it'd be 15 squared plus 25.98 squared square root times 10 to the 3 meters. When I do that, I get 15 squared plus 25.98 squared gives me 899.96 square root times 10 to the third meters. Take the square root of the answer, and that gives me 29.9993 times 10 to the third meters. Okay, so now A hat, that means it's a unit vector, is negative 15 times 10 to the 3 over 30 times 10 to the 3. Notice that 29.9993, that's really 30 to as many sig figs as we use. That's the I hat direction, plus this one, which is essentially, you can probably call that essentially 26. So that's going to be negative 26 times 10 to the 3 over 30 times 10 to the 3. And that would be my J hat vector. So this one's actually essentially going to be negative. Oh, I don't know how that happened. Just changed to that. Okay, it's going to be negative 1/2 I hat plus 26 over 30. 2 goes into that. That'd be 13/15. So I could say 13/15 J hat, and they're probably pretty close to being magnitude of 1. That has to be a negative in between there, though. Sorry. Okay. So all you really have to do is now take that magnitude that we had calculated in the previous problem and multiply it by that A vector, so that F equals G M1 M2 over R squared times A hat, which is a unit vector. Notice how even the unit meters disappeared. That actually makes your formula into a vector formula. That's something you can do if you feel comfortable. That'd be great. If you don't feel comfortable, don't worry about it. It's not that critical, but it is something that can give you a little more confidence when working with vectors, the more stuff with vectors that you do. So I wanted to cover that with you. The only things that I really need to tell you now about this, and I'm going to let you go. I know we've got 20 more minutes, but I got to give you at least 10 for the break that we normally have. I'm going to stop sharing for a second here. Actually, I'm going to stop sharing permanently. So the other things we need to know is things like what's a geosynchronous orbit? Have y'all heard of geosynchronous orbits before?
I've heard of it before.
So what it means is in sync with geo, which is our Earth. So a geosynchronous orbit is the orbit that, for instance, DirecTV there's several DirecTV satellites, by the way. There's several Dish Network satellites, but all of those satellites are in fact in geosynchronous orbit. And what that means is it's along the equatorial plane of the Earth, but it's orbiting at exactly the same rotational rate as the Earth. So in other words, it's far from the Earth, but it completes one orbit in 23 hours, 56 minutes, which is basically a sidereal day. The time required for the Earth to complete a 360-degree rotation is called a sidereal day, which is a little shorter than a solar day, which is from noon to noon. A solar day is 24 hours. A sidereal day is 23 hours and about 56 minutes. Because it turns out that we move, since the Earth is orbiting the sun in about 365 or 365.249 days, then that means if you divide 360 degrees by 365.99 or whatever, you end up getting 0.986 degrees. That 0.986 degree is the extra amount the Earth has to rotate for a shadowless pole to be directly under the sun again, to be a shadowless pole. Okay, so that's 360.986 degrees instead of 360 degrees, but that's what we call a day. So that's 24 hours because that was the first discovery of a day we had. Now, if you want to see how long it takes the Earth to rotate from here to here, in other words, the pole's sticking up and pointing at a constellation, let's say Cancer. It's pointing at the constellation Cancer. Now you wait, it's 8 p.m. say, and you wait till that same pole points straight to the constellation Cancer, a very specific point in that constellation Cancer. Even when you do that, it turns out that'll happen at 7:56 p.m. the next day. So 8 p.m. one day, 7:56 p.m. the next day. So that's what a sidereal day is. So when you do a geosynchronous orbit, you really use like 23 hours, 56 minutes for it to complete its orbit of one period. And that keeps that particular satellite over a particular point on the surface of the Earth. So when you, for instance, see, lately I've been seeing a commercial for a internet service where you can get it from a satellite, and they'll say, all you need is a clear view of the western sky. What that means is they're probably running that commercial here on the East Coast. If you were maybe in Nevada, they might actually say, all you need is a clear view of the eastern sky. Because maybe that satellite is directly over Kansas, say Kansas City, Kansas, in fact, which is about the center of the United States. If that's the case, then people on the East Coast need a clear western horizon, and people on the West Coast need a clear eastern horizon. Does that make sense? So that's one of the types of orbits that you have. You can also look for ways that you can put things in orbits where, let's say, the Earth is pulling on a spaceship when it flies directly towards the moon, but the moon is pulling on it as well with a force of gravity. So a typical problem we might ask is, at what point between the Earth and the moon does an object feel no gravitational force? Well, in principle, it might feel a gravitational force from Mars and from the sun, but those are all so much farther away than the Earth and moon would be for that ship that you can assume they're like in the 12th decimal place and don't worry about it. Then you just set the two forces, which would be G times the mass of the ship times the mass of the Earth over the distance squared, equal to G times the mass of the moon times the mass of the ship, divided by D minus X squared, where D is the distance between the center of the Earth and the center of the moon. And when you set that up, that allows you to solve for X. And then you'd have the sort of the equilibrium point between the Earth and the moon. Does that make sense? Okay, so that's about it. I'm going to go ahead and call that completion of chapter 6. As you can tell, chapter 6, a lot of times, a lot of people don't even cover it in this course, but I don't like not covering it. I will tell you that Einstein comes along, and when he does, he's still got a problem with his action at a distance, this ability of something to reach out across space with us not seeing it and pulling on something that's not touching. What Einstein ended up concluding was that, in fact, the space that we know of is not three-dimensional. It's actually four-dimensional. It's left, right, which might be X. It's in, out, which might be Y. It's up, down, which might be Z. Notice they're all three perpendicular to each other. Okay, that's 3 dimensions. What he said was, in fact, the 4th dimension is time. And believe it or not, that's also mutually perpendicular to the first 3. Okay, and in that 4-dimensional space-time, as we call it, it turns out that matter tells space how to curve, and space tells matter how to move. So just like a trampoline with a bowling ball on it, the trampoline is going to pucker down for the heavy bowling ball. And in fact, if you shoot a BB to roll along the trampoline, just missing the bowling ball, it'll go into that well and go around like this, just like the planets going around the sun. Of course, over a small period of time, it'll spiral in and go to the center, but that's because of the friction between the trampoline and the BB. But in space, there's just very little anything. I mean, you're likely to see on the order of a few atoms in a 1 meter by 1 meter by 1 meter cube. So they get almost no friction. But in fact, that's what Einstein concluded. And in fact, he had to show that it, was actually useful and predicted results that were useful. And one thing he did was predicted the bending of starlight from a star during an eclipse. That was shortly thereafter proven to be true by Arthur Eddington. And then he also explained the precession of the perihelion of Mercury. So if you think about the perihelion, that's that spot where Mercury is closer to the sun. And what they found is that spot was actually moving around the sun over hundreds and hundreds of years. And they could explain that because of some of the other bodies acting on Mars. They could explain that with Newtonian gravity, but it was off by like a factor of 2. But when Einstein did it, he got exactly the right answer. And then he made other predictions that we only just discovered in 2015. He predicted more or less the existence of black holes. He sort of did, but the main thing is the first solution found did. He predicted gravitational radiation, which we just found in September of 2015. And he, which is actually gravity waves. And he, predicted basically what we would see if 2 black holes collided, or 2 black holes, or a black hole and a neutron star collided, or 2 white dwarfs collided, all this different stuff. All of those things we can now predict with Einstein's general theory of relativity, and they match exactly what we're getting from LIGO. We can't do the white dwarfs yet, but we can do neutron stars with black holes. And I think we can do neutron stars with neutron stars. So that's about it. You guys are free to go. I'll wait for the last person to leave, and then I'll sign out. But have a good one, and I will talk to you all Monday. Remember, or excuse me, Tuesday. No, you are my Monday class. So remember, Monday we do not have class. That's our celebration of Juneteenth, which actually occurs on Sunday, but we still have the day off on Monday the 20th. So no class on Monday. And I think we're actually supposed to be having a test during lab on Wednesday. So start preparing for that for test 3. I'm going to put the practice test up today. And that'll cover chapters 5 and 6, which is this one. Actually, I might have to move that back because we just did chapter 6, and I want you to have a chance to ask questions. Pay attention to your email. I'm going to have to make a decision about that. I might get Kevin to move it back, or Mr. Mitchell to move his lab forward, and then we have it Monday of next week, the week after, I mean. Okay, so watch your email, and I'll see you guys. Thanks everybody for coming. I'm sorry for the problems we had at the beginning, but have fun, have a nice weekend, stay safe.
Have a good weekend, Professor.
Thank you.
You too, thank you. Gabriel, do you have any questions? Or is it Gabrielle? I don't think I've met you yet. All right, it looks like Gabriel's not here. Y'all have a good one. Bye-bye.